Isomers part 2, or continued. So before we continue, let's just very quickly do a quick sort of reminder of where we were, right? So let's first go to our glucose molecule is the example that we're using. So we talked about how we can have L-glucose and we can have D-glucose, right? And so the D-glucose is the right-handed version of glucose. So let's just make sure we draw, and we'll use the Fisher projections first. So in the Fisher projection, we have 6 carbons. And the top carbon has the carbonyl group on it. The bottom carbon is just the CH2OH part. And then what we have to do is look at the occurrence of the hydroxide or the hydroxyl functional groups along the side of the molecule. And if we do the same thing, we look at L-glucose, six, that's really the only difference, right? Okay, so where do they go on D-glucose? There's more on the right-hand side, right? So where are they? Which carbon? This is carbon 1. So where are the OHs on D-glucose on the right-hand side? Yep. 2, 4, and 5. So if we put 1 here on carbon 2, and then skip 1 and put 2 down here. So you can kind of just use that as a little remembering aid, right? And that means the other one goes on this side. There's only 1, right? And then H's fill in the gaps. Okay? That's D-glucose. L-glucose would be the exact opposite arrangement. So you'd put your OH here and your H there. You reverse each one, and you'll see that what happens is you get more of them on the left-hand side. So those are the 2 Fisher projections of these molecules. And of course, we could also look at the Haworth projection. The only difference would be instead of them being side to side, we would have more OHs on the top versus on the bottom, right? Right. So rather than draw those as well, those are in your book from yesterday, so you can go back and look at those. So this is D and L. That's the difference. It's like your right and left hand. Okay. So the new thing we're going to learn is this. Extend the page. So now what I'm going to do is draw some projections. I'll draw some Haworth projections. But you know what? Okay, so let's look at just D-glucose alone before we get into the confusing part. So let's draw a picture of D-glucose using the Haworth projection. So basically, what we have is the 6-sided molecule. Oh, remember to put the oxygen in there because put him in red. He's not a carbon. Remember, the corners are carbons, but we got to put the oxygen in. And then we put the thicker sort of line here at the front, like that, like a triangle shape kind of, showing, sticking out, and then we go across the bottom and fill it in like this. So something like that. That's a very thick version of the Haworth projection of glucose. Then we take our I'm going to go thinner here, and we put our bond, all the spots, the corners that exist, and then we can write here the CH2OH part, which is up here. And then what we're basically going to do is we're going to put all the OHs in their spots. Okay? I'll do it from memory, and you just correct me if I'm wrong. But when we do this one, I believe we had an OH here, and another OH here, and then we had the OH here, right? And one on the bottom. Is that our picture of D-glucose from yesterday? Good. So we have 3 on the bottom and 1 on the top. 3 going down, 1 going up. The rest are H's. Okay. Not only, yep. Let's reverse those. Okay, well, you know what? To be safe, I will just look it up real quick. You are right. Yeah, that's true. That should go here. Good. We'll correct that. OH here and OH here. That's better. Okay. Go back to thin line. But it's still 1 up and 3 down. That's the main thing. Okay. Now here's what can happen. D-glucose can also take on a different form where the bond on the end here rotates. And we did that with the, I'm going to pause for a second and play with the models. Okay, so let's draw another Haworth projection right beside here. And let's draw this with our O and our little triangle. Whoops, let's go back to black. Like that. And let's make the 3D part down here. The board is not 100% calibrated. Fix that later. It's making it hard for me to do the 3D when when my finger isn't touching exactly where it's drawing. But we'll make do. So something like that. And then we put in our little lines. And of course, you know, we draw these things 1,000 times and they become commonplace. We put our CH2OH up here. Now watch this. This OH is still here. The OH here is still where it is. The OH here is still where it is. But the OH on this side is flipped, like I showed you with the model. It could go either way. It could go on either of the carbon bonds. So what we have now is a D-glucose, but we have a flip of just one of the OH groups. So we can flip them all and make D and L glucose, or we can take glucose and just flip one and make these two versions. So there's like subgroups of isomers. And these two versions are called, when they're both on the bottom, alpha D glucose. Or sometimes just alpha glucose for short, because when we're talking in biology, D-glucose is the more common isomer that's used in biological systems. So we tend to just assume we're talking about D-glucose all the time, unless we specifically say L-glucose. So sometimes you'll just see it as alpha glucose, but it should be called alpha D-glucose. And this other version is called beta D-glucose. Right? Or sometimes just beta glucose for short. So more complicated. More complicated. And of course, you have to remember, as we discovered these things, we made up names to accommodate them, not realizing that we would later discover even more and that our names might not make that much sense and it gets complex and complicated. If you were to go back in time, knowing everything we know now and create a naming system, you'd make it much simpler. But because we're naming as we discover, right? We name something, and then we discover something new, and rather than go back and change all the names, we create a new name or a new subcategory, or we add an alpha or a beta or a little letter. And that's why it gets so complex. So that's just the way it goes. So look at these two pictures for a minute, and drill into your mind what makes them different. And it's simply this. This is the part that makes them different. One is up and one is down. Right? What I like to do is I like to focus on the two ends. So I focus on this side and this side of the molecule. And I remember that if they're both down, it's alpha glucose. Over here, if they're one up and one down, it's beta glucose. Okay, and you can see that picture in your textbook on page 30 at the top. There's a bunch of different isomers and things that are drawn there, giving you that idea. Okay? So that's what the alpha and the beta means. All right. we can make it even more of a pain, but maybe we won't do that just yet. Well, why not? What the heck? Okay, you got those in your head. Now watch this. Just to make it more complicated, let's draw one more. So back to here. I'm going to get my thin line. I like that better. Okay, so we go here. We go here. We put our oxygen atom in there so we don't forget about them. And then we go here. I got my thick line again. Smart boards are not very smart, are they? Okay, and then we can color, or just sort of give us the color this in. Now, a lot of times you don't bother doing this coloring in when you're drawing these pictures. You just draw it like a hexagon with lines. But that shading actually does help. It does make a big difference in seeing the up and downs of the molecule. So CH2, COH. Okay. So far, if we're looking at the two ends, the right and left sides, we saw that if the OH is down and down, we have alpha glucose. If it's down and up, then we have beta glucose. But it's also possible to twist them both so they're both up. If you look on page 31, you can see there's a molecule. Well, you can't really see it by itself. It's actually linked to something else in there, but it's called galactose. And so it has a different name. So OH, up, up, these two the same. Both up. So again, I'm looking here and here, and I see that both of them are up. This one has another name called galactose. Yeah. Different forms of glucose, yeah. Different isomers. So again, that means that they are two or many different arrangements of the same atoms that work. And when I say work, what I mean is that they are relatively stable because the electrons are far enough away from each other and pushing and pulling in those shapes. Now, it's true that some are more stable than others, like D-glucose might be slightly more stable than L-glucose, or alpha-glucose might be slightly more stable than beta-glucose. But they're stable enough that they can all exist. So now we have created 3 different isomers of this D-glucose. Yes, ma'am. No, so HO and OH is not a difference. It's just one backwards or one, right? So yeah, it all depends. So when you do that, let me show you. What you're doing here is you're trying to show that there's an oxygen and a hydrogen attached to that carbon. The oxygen is always attached to the line, and then the H can go on either side. So it's really just what's convenient. See, HO and OH, it's the same thing, just backwards. So that's not a change. It's only these two things on the end, and they're up and down positions. Both down, what is it? Both down, alpha glucose. One up, one down, beta glucose. And it's actually the left one down and the right one up. Okay, that's important. And then if both up, it's called galactose. Yay, organic chemistry. And so these are all isomers of glucose. I'm also going to show you another isomer of glucose that's going to be quite important to us. And what? No? You're not done yet? Okay. I'll just pause the video. All right. One more crazy isomer. This one is a 5-carbon. So let's, actually maybe 2 of them we might do, but this is the one that's the isomer. So we'll do this one first. So let's pick this, let's get our thin line, and let's go, and let's make a line like this. We're essentially going to make a pentagon. And the oxygen is going to be at the top. So let's put him in right now so we don't forget about him. That's where the O is going to go. Right? There's always an O in the link. Oh, it's supposed to be black. Fix that. Let's go here. Black. Every time I change pens, I have to go back and change thickness, which is kind of a pain. There. So there's the 5-carbon ring structure that we want. And if we were drawing it as a proper projection, we'd make the front part a little thicker, as usual. Right? And then we go like that, that, and sort of thicker here, this end, so something like that. Good. And then we put our little lines in here at each of these spots. So because it's a 5-carbon sugar, we have the CH2OH on this side. And we also have another one on the other side. So this one goes here. Now watch. Watch this. Watch Miranda. Okay? HOCH2. Just the same thing backwards. You can write them backwards. It's the same thing. And the reason we do that, actually mine isn't quite right because the C should be above the line. The C is the thing that's touching the line. So to do it right, you put the C here, H2. And instead of writing the OH on this side where it's crowded on the right, we just stick it over here. That's the same as the other one, just written backwards. All these little details that make organic chemistry complicated to learn, right? Okay, and now we need to put some OHs in. So we're going to put an OH down here, and then we're going to put an OH up here. I'll write it backwards so it fits better. And then we have one more right here, and the rest are H's. Okay, and if you count up, you know what, I'm going to put the H's in this time because we're going to count. So let's count our carbons. There are 4 in the loop, 4 corners, because one's an O, 4 corners in the loop, and then there are 2 sort of on the outside on these little groups on the CH2OHs. So there are still 6 carbons, so we still have C6. And if I've done it right, we should have 12 H's. So let me go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we still have H12. And if we count the O's, there's 1, 2, 3, 4, 5, and the one in the red one in the ring, O6. H12, O6. So we still have the same number of atoms as glucose, but again, in another arrangement that happens to be stable enough with all the atoms happily pushing and pulling on each other. This is sort of one of the resting spots that they will fall into. And this guy is called fructose. So fructose is an isomer of glucose. It's the same atoms rearranged in a 5-carbon shape rather than a 6-carbon shape. But because its shape is different, it acts very different, so it deserves a whole new name, and it's a whole different molecule because it behaves very differently. All right. So now we've seen that this glucose molecule can come in left and right forms, L and D. It can come in, if we just look at the D alone to keep it simple, the D can come in the alpha or the beta version with the changing ends up and down. And it can also come in another 5-carbon ring shape called fructose. All of these are the same C6H12O6. So even the molecule glucose is more complicated than we thought when we were writing it like this in grade 9 and 10, when we were writing about respiration and photosynthesis. It's complicated. And it's all because of shape. Let me pause the video and then I'll take your question. So those are the isomers of glucose that we're going to be looking at. Okay, and in our next video, we'll look at carbohydrates more generally.